In this session, we will talk about how to calculate the pH at any point along a weak acid strong base titration curve. We'll do this example and then you can think about how to apply this to other types of titrations. I would argue that this is one of the most difficult things that you're going to do as part of Chem 132. And the thing that makes it difficult is that we really bring together all of the things that you know about acid-base chemistry. So to help support that, you can read in OpenStax Chemistry section 14.7, and I really strongly urge you to check out the LibreText article that is linked in the show notes. Okay, so here's your guideline to how to calculate the pH during a weak acid strong base titration. So as you can see, before the addition of any NaOH, so at 0 milliliters added, what we have is a solution of a weak acid. So you know how to use an ice table to calculate the pH of a weak acid. Then we'll see when we start adding NaOH, but before the equivalence point, we will have partially neutralized our acid so that we'll have a combination of the weak acid form and the conjugate base form. That makes a buffer, and we can use the Henderson-Hasselbalch equation to calculate the pH of that mixture. At the equivalence point, we will see that we have a solution of a weak base, and we can once again use an ice table to calculate the pH of that solution. Finally, after the equivalence point, when the weak acid is the limiting reactant and the added OH minus is in excess, we'll see that it's only the excess that makes a difference in the pH. Okay, so here's our example problem. Consider the titration of 40 milliliters of 0.250 molar HF hydrofluoric acid, which has a Ka of 3.5 times 10 to the minus 4. And we're going to titrate that with 0.200 molar NaOH, 0.2 molar NaOH. And our task is to calculate the pH after 0, 25, 50, and 80 milliliters of NaOH have been added. So, what makes this tricky is that all of these problems look the same, but as you'll see, the way we calculate the pH is very different based on what we have. So, let's think about the chemical reaction that's happening here. When we add the NaOH to solution, we know that NaOH is a strong base, so it is going to dissociate completely into Na plus and OH minus. Now the Na plus is an inert, neutral spectator ion, so we will think of this NaOH as being a source of OH minus, which is going to affect the pH of the solution. As we think about how this is going to affect the titration, we realize that these problems all have two parts. The first part is neutralization. And in a neutralization reaction, we have an acid here, HF, reacting with OH minus to completion to form F minus and water. So the first step is going to be to neutralize, to do the neutralization reaction and figure out what we have left over in the solution after this happens. And then the second part is going to be calculate the pH of that solution. Some things we might want to think about here. So we said that the Ka is 3.5 times 10 to the minus 4. If we can find the pKa of that solution by calculating negative log of Ka, which we'll find here equals 3.46. That might be useful. We also know that as we're thinking about this, we're going to want to know how many moles of HF we're dealing with, not just the volume. So we know that we have 40 milliliters of 0.25 mole per liter. And we're going to find that it's easier if we do this problem, makes the numbers easier to work with, if we think about millimoles. So if we watch here, if we've got 40 milliliters times 0.250 millimoles per milliliter, then we see that that means we have 10 millimoles of HF present in our solution. Okay, so with those things in mind, let's consider the first question. Calculate the pH of the solution after 0 milliliters of NaOH have been added. Okay, so like we said before, the first thing we need to think about is the neutralization reaction. So we've got HF plus OH minus becomes F minus plus water. And we said that neutralization reaction, it goes to completion. So we also said that we have 10 millimoles of HF present in solution, and that we've added 0 millimoles, 0 times 0.200 molar, 0 millimoles of OH minus. So that means that after this reaction happens, or rather doesn't happen, we're going to have 10 millimoles of HF in solution. Okay, so now that we've done the neutralization reaction, now we need to calculate the pH of whatever is present in solution. So we've got 10 millimoles of HF and really nothing else. So the principal reaction, the one that affects the pH, is going to be the acid dissociation of HF. So HF plus water goes to H3O plus F minus. And we said we have 10 millimoles in 40 milliliters. And remember, so if we want to calculate the pH of a solution of a weak acid, we're going to use an ice table. And for the ice table, we want concentration. So we're going to use 0.250 molar. All right, we know that initially we have basically no H2O plus and no F minus. And so we can complete our ice table. Okay, in order to solve for X, which is going to give us the H3O plus concentration that we can use to calculate the pH, we are going to substitute into the Ka expression. Where the Ka is 3.5 times 10 to the minus 4. Now, you could try the small x approximation here if you wanted, but spoilers, it's not going to work. So instead, we're going to develop a quadratic equation and solve it. The quadratic equation I get is x squared plus 3.5 times 10 to the minus 4x minus 8.75 times 10 to the minus 4 equals 0. And I find that the chemically relevant value of x is 0.029. Now, that value of x equals the value of H3O plus, and so we can calculate the pH equals negative log of 0.029, which means the pH equals 1.53. Okay, so we've solved for the pH at the beginning of the titration, after 0 milliliters of NaOH have been added. All right, let's go on to the next point. So now, new problem, let's calculate the pH after 25 milliliters of NaOH have been added. Okay, so we got 25 milliliters times 0.200 millimoles per milliliter of NaOH. That gives us 5 millimoles of OH minus. So let's put that into the first part of our problem, which is the neutralization reaction. So HF plus OH minus goes to become F minus and water. Okay, we know we start with 10 millimoles. So we're kind of imagining going back to the beginning of the titration, and now we've added 25 milliliters. So we started with 10 millimoles of HF, and we're adding 5 millimoles of OH minus. Initially, we start with no F minus, and water doesn't really matter. Okay, so look here. The OH is the limiting reactant. Here we go. So this is the limiting reactant. So that means that we're only going to make as much as we have of that one. So that means we're going to lose 5 millimoles of HF and 5 millimoles of OH minus, because those have a 1-to-1 stoichiometric coefficients, and that's going to produce 5 millimoles of F minus. So at the end of the reaction, we'll have 5 millimoles of HF, no OH minus, and 5 millimoles of F minus. All right, so now we need to figure out what's in solution and calculate the pH of that. So here we have both HF and F minus in our solution after the neutralization reaction. This means we've got a weak acid and its conjugate base. This is a buffer. We can use the Henderson-Hasselbalch equation to calculate the pH. Okay, so pH equals pKa plus log of F minus, the base form, over concentration of HF. So we notice that these are concentrations. So we're going to need to figure out the total volume in addition to just the number of millimoles. All right, so we calculated before that the pKa here is 3.46 by taking negative log of Ka. And if we put in the F minus concentration, so we have 5 millimoles of F minus divided by a total of 65 milliliters, which we got from the 40 original plus the added 25 milliliters. Okay, we'll divide that by the 5 millimoles of HF present in the same 65 milliliters. Okay, put all that together, and oh look, we see that the overall that equals 1. The log of 1 is 0, and so here the pH equals 3.46, which is also the pKa. Alrighty, so analyzing this a little bit, it turns out that because we have added half as much OH minus as the HF we started with, this is called the half equivalence point. At this point, the pH equals the pKa. If you had noticed that, you could have skipped directly to the pH equals the pKa, but using the Henderson-Hasselbalch equation, we know that we could also solve for the pH when we had a mixture of F minus and HF where they weren't equal. Okay, so here we've calculated the pH after 25 milliliters of NaOH have been added. Time to go on to the next point. Okay, new problem. We're now going to calculate the pH after 50 milliliters of NaOH have been added. So, 50 milliliters of NaOH times 0.200 millimoles per milliliter means that we have 10 millimoles of OH minus. All right, once again, we put that into our neutralization reaction. HF plus OH minus becomes F minus plus water. We know that we start with 10 millimoles of HF and 10 millimoles of OH minus. Okay, in this case, neither of these is the limiting reactant. So they're in their stoichiometric ratio. So both of them are going to react by 10 millimoles. And we're going to produce 10 millimoles of F minus. So at the end, we will have no HF left, no OH minus, and 10 millimoles of F minus. So that means that the concentration of F minus will be 10 millimoles divided by the total volume, 40 milliliters, plus the start with, plus the 50 milliliters we added. And so the concentration of FF minus will be 0.111 molar. Now, F minus is the conjugate base of HF, a weak acid. So that means that F minus is itself a weak base. Since that's the only thing that we have in solution that can affect the pH, we're going to calculate the pH of this solution by thinking about the dissociation of F minus. So F minus can react with water to form HF and OH minus. This reaction is written in the form of Kb, which we can find using Kw. If we do that, we find out that the Kb for HF is 2.9 times 10 to the minus 11. Okay, we can calculate the pH using an ice table. Our initial concentration of F minus is 0.111 molar. We have no HF and negligible OH minus to start with. And so you're getting pretty good at these ice tables now. And we see that if we can find X, we can calculate the OH minus concentration, which will lead us to the pH. Okay, so once again, we'll sub into the Kb expression, X squared divided by 0.111 minus X. And we see here that Kb is really, really small, 2.9 times 10 to the negative 11, compared to the 0.111 molar. So here we can assume that this is about the same as X squared divided by 0.111. And if we do that, we get that, we solve that, we figure out that X equals 1.76 times 10 to the minus 6. And if you check your assumption, you see that X is really small compared to 0.111. Okay, so this X will give us the OH minus concentration. And then there's a couple of ways that you could calculate the pH. Either you could calculate the pOH, which equals 5.75, and then subtract from 14 to find the pH, which equals 8.25. Or you could use, remember that Kw equals the OH minus times the H3O plus concentrations. And so you could find H3O plus using 10 to the negative 14 divided by 1.76 times 10 to the minus 6, and then calculate negative log of OH that way. Okay. So we have calculated the pH at after we've added 50 milliliters. So a little bit of reflection on what's going on here. This point where we have equal amounts of HF that we started with and OH minus that we added means that this is the equivalence point of our titration. At the equivalence point for a weak acid, we see that the pH is greater than 7, that the pH for a strong acid, strong base titration always equals 7 at the equivalence point. We see that here that we're a little bit more basic than that, and that's consistent with the fact that when we do this titration, we end up with a weak base. So that solution is a little bit basic. Okay, time to go on to the last point. Oops. At this point, we're going to calculate the pH after 80 milliliters of NaOH have been added. So we're getting pretty good at this. By now, we can calculate how much OH minus is added. 80 milliliters times 0.200 millimoles per milliliter means that we're adding 16 millimoles of OH minus. We put that into our neutralization reaction. HF plus OH minus goes to F minus plus water. We know that we started at the beginning with 10 millimoles of HF, and we added 16 millimoles of OH minus. Now this time, the HF is the limiting reactant. So all of the HF will react, and a stoichiometric amount of OH minus will react and will produce that amount of F minus. So after the neutralization, we'll have no HF left, 6 millimoles of OH minus, and 10 millimoles of F minus. Okay, so now we have to figure out how to find the pH of this solution. So we got two things here that could affect the pH. We have both we have OH minus, and we also have F minus, which we know is a weak base. And we have OH minus, which is equivalent to having a strong base. So it turns out that the strong base is going to be the principal source of OH minus. Remember, we found that the Kb for F minus is equal to 2.9 times 10 to the minus 11th. So this is a really weak base. It is not going to significantly contribute OH minus to the solution, especially not compared to the 6 millimoles of OH minus we have. Okay, so we're going to use that OH minus to calculate the pH. Okay, so the concentration of OH minus in the solution will be those extra 6 millimoles divided by the total volume. So the 40 milliliters we started with plus the 80 milliliters that were added. And so we're going to get that if we put that into the POH formula, negative log of 6 millimoles divided by 120 milliliters, we get that the POH equals 1.3, and so that means that the pH equals 14 minus that, which is equal to 12.7. Okay, so we see that this solution is quite basic because we have extra strong base added. So if we analyze this a little bit, this is after the equivalence point. And we see that only the excess OH minus here affects the pH. Alrighty, so we've calculated the pH at all 4 of those points that we started with. Now we can use all of that to sketch the titration curve. So if we remember back to our titration curve is going to be the pH on the y-axis versus the milliliters of added 0.2 molar NaOH. Okay, so when we added 0 milliliters, we saw that the pH of our solution was about 1.5. So we'll put that. Okay, hang on. Sorry, we're going to back up for a second. This is milliliters of added 0.2 molar NaOH. And the y-axis is pH. Okay, so let's try again. We got 0.2. We got at 0 milliliters added, the pH was about 1.5. At our next point, which was 25 milliliters, we saw that the pH was 3.46. So let's call that right about there. We saw that at 50 milliliters added, the pH was 8.25. So maybe right in there. And then finally, at 80 milliliters added, the pH was 12.7. Right in there. Okay, so if we think about what our titration curve is going to look like, we can connect the dots. We're going to start at 0 milliliters, and we'll see that through the buffering region, our titration curve will flatten out. We get very little pH change with added OH minus. And then close to the equivalence point, we've exceeded our buffer capacity, and the pH changes very rapidly as we go through the equivalence point. And then finally, it levels off as we approach basically the concentration of the OH minus that we're adding. Okay, so there's our titration curve for the titration of 0.25 molar HF with 0.2 molar NaOH. In this video, we've talked about how to calculate the pH at any point along a weak acid, strong base titration curve.